Good afternoon, ladies and gentlemen. Thanks for the introduction. Today I would like to talk with you about efficiency of electron beam extraction to the atmosphere in an accelerator based on ion-electron emission. Beams of charged particles have unique properties. That is why accelerator technology is relevant for both one-dimensional and applied works. One of the technology's nuances is generation of cross-section electron beams. These beams are characterized by cross-section area about of 1000 centimeters square, and these beams can provide high performance due to the large processing area. There are several main types of low energy electron accelerators with large cross-section beams. These with thermometers, with plasma cathode, with explosive emission cathode, and with ion electron emission, or based on non-self-contained high voltage glow discharge. The object of research belong to the last type, and advantages of accelerator based on ion electron emission are relative simplicity of design, lack of heating elements, long lifetime and stable performance, beam current control without changing accelerating voltage, moderate requirements for the pumping group, and auxiliary discharge on the ground side. These beams are applied for photoradiation processing, curing of polymer coatings, pumping gas lasers, sterilization of medical products, etc. One of the tasks of all accelerators with large cross-section electron beams is increasing of extraction coefficient. This coefficient is usually defined as ratio of beam current in the atmosphere to current in the accelerating gap. For increasing of extraction coefficient, used the reduction of electron beam current losses. For this task, achieve optimal ion electron optical system, and there are two main methods. First of all is calculation and creation of electrode design, and changing of emission plasma boundary. The first method is difficult and make it possible to create high extraction coefficient only in narrow range of operation pressures and at certain conditions of beam generation. That is why we have chosen changing of emission plasma boundary for increasing the extraction coefficient. So, purpose of this research work was to investigate the influence of auxiliary discharge mode generation, direct and pulse periodic with frequency up to 100 kHz, on the extraction coefficient, on the extraction efficiency of electron beam in the atmosphere. The second task determine the extraction coefficient at the direct mode, generation of auxiliary discharge at the pulse periodic mode, and provide colorimetric measurements of average power output coefficient. Because of studied accelerator based on secondary ion electron emission, we need to address what it is. Ion electron emission is electron emission from the surface of a solid when it is bombarded with ions. Efficiency of this emission is characterized by coefficient gamma, which depend on the energy of incident particle, type of ions, and substrate material. In this slide you can see photo and design of the studied accelerator. Its parameters are electron energy up to 150 kV, beam current up to 40 milliamperes, current density up to 50 microamperes per centimeter squared, and beam dimension 35 times 65 centimeters. The studied accelerator has two main parts. The part in which auxiliary discharge is generated for creation plasma anode, and part that is responsible for combustion of non-self-maintained high voltage glow discharge. The The role of auxiliary discharge is played self-contained glow discharge, in which two tungsten wires as an anode and walls of the vacuum chamber as a hollow cathode of discharge. These parts are separated by anode grid and extracted ions from the anode plasma accelerated in the gap bombard the surface of high voltage cathode, and as a result of this bombardment there appear electrons which are also accelerating in this gap, pass through the plasma anode, through the thin metal foil and output in the ambient atmosphere. Beam current are registered with help of collector. There you can see electron beam outputted in the atmosphere at the different accelerating voltage. In the right picture you can see photo of helium gas plasma of auxiliary discharge. In the start of this research work, we measured oscillograms of currents at the direct mode of auxiliary discharge and quantified extraction coefficient. You can see that this coefficient is low and is up to 0.25. This coefficient is quantified as ratio of amplitude values of current at the different accelerating voltage. You can see that in range of discharge current from 30 milliamperes to 80 milliamperes, extraction coefficient doesn't change. That probably due to slightly changing of ion-electron optical system. Low extraction coefficient, low value of extraction coefficient due to a lot of electron beam losses. These losses occur on anode grid, on output support grid, and on output metal foil. How we can see, about 60% occur on the anode grid and output support grid. For changing plasma boundary and improving of ion-electron optical system, we used pulse periodic mode of auxiliary discharge, and there you can see the oscillograms. We quantified extraction coefficient, and you can see that in this mode we can change amplitude of discharge and pulse duration due to stabilization of average value of discharge and due to controlling of pulse duty factor. You can see that at the duty factor 80%, extraction coefficient is low and equals about of 0.2. That's due to similar ion-electron optical system with a direct mode, but at the less duty factor extraction coefficient is raised and equal up to 0.55. That means changing of ion-electron optical system, and it's proven. The minus of this mode is at the moment of pulse of generation discharge current, beam current is low, but current in the accelerating gap is present. Therefore, extraction coefficient in this moment is very low. Presence of current in the accelerating gap at the pulse of discharge generation is explained by decay of auxiliary discharge plasma. we put in the plasma cylindrical collector and measurement ion component of discharge, and we saw that its component doesn't equal 0 at the pulse. Then we measured frequency dependence of pulse periodic mode, and we saw that at frequency 50 kHz and more, extraction coefficient is up to 0.25, but at the less frequency, about of 20 kHz, extraction coefficient is raised. In the figure 17, you can see that at frequency up to 30 kHz, discharge voltage is high. Most likely at the high frequency occur constant component of discharge, and this component decrease amplitude of discharge current and therefore decrease discharge voltage. High discharge voltage leads to increasing of width of cathode layer, and probably because of this appear changing of ion-electron optical system, and extraction coefficient in the pulse periodic mode increase. Since we measure extraction coefficient as ratio of amplitude values of current, we provided colorimetric measurement of outputted power beam. We used water colorimeter, and we used role of the colorimeter was played radiator from Was Patriot, because it's ideally for beam sizes, and we measured temperature of water and quantified outputted power of the electron beam. Then we calculated power in the accelerating gap and quantified power output coefficient, and we saw that at the pulse periodic mode power output coefficient more on the 5%. So the coefficients of electron beam current extraction from the vacuum in the atmosphere are determined for different modes of plasma generation. It's shown that an indirect mode of electron beam generation at an accelerating voltage of 150 kilovolts, the beam extraction coefficient does not exceed 0.25. The possibility of increasing the extraction coefficient to 0.50 at the same accelerating voltage was demonstrated without making changes to the design of the accelerator, but switching to a pulse periodic mode of plasma generation. Using the presented pulse periodic mode made it possible to increase the power output coefficient from 0.15 to 0.2. And our plans for the future to provide probe measurements of auxiliary discharge and simulate plasma boundary in the different modes of auxiliary discharge. Thank you.
Thank you for the presentation. My question is important for the competition of young scientists. Your report have 5 sources besides you, and what is your role, your impact in this work?
I provide these experiments and do this work.
You made this installation yourself?
We, with our team, improve this accelerator for the next purposes.
Thank you.
When you use pulse periodic regime mode, there is a decay time between the pulses, the decay time for plasma. So the conditions for the information is not optimal for this case, and you should have lower values of beam efficiency extraction. I do not understand why you have a higher efficiency at the pulse periodic mode.
In the pulse periodic mode, we stabilized average current, and in this mode, amplitude of discharge increase, and therefore plasma boundary change and change of ion-electron optical system.
It's clear that the form of the plasma boundary will be different for DC and for pulse region. Maybe in pulse region the form of plasma boundary is not optimal. That is the reason.
In the direct mode, optical system doesn't optimal. Yes, and we improve this system.
Thank you.